Okay, so let us continue our discussion with the next example. So this is example 3.1.32. So in this example, the step will be the same as the previous one, but the statement, we are going to change that. So let A be the set of these three numbers for each x in A and for each element x in A and each object y, we define px comma y to be the statement y is equal to 1. So this statement does not actually depend on x, but you can think of it as depending on x in a trivial way, specifically in the sense that it really does not depend on x. However, it depends on y, and it simply says that y has to be equal to 1. Then we say that p of x comma y is true. So irrespective of the value of x, this will be true if y is 1. Okay. Clearly, for each x belonging to A, there exists exactly one y for which px comma y is true, and that y is equal to 1. No matter what the value of x is, as long as we have y is equal to 1, then p of x comma y is true. Specifically, the condition that we have to verify in this case, that for each x in A, there is at most one y for which px comma y is true in this case. Exactly 1 means at most 1 also. Hence, by axiom 3.6, the following set exists. The set of all y such that px comma y is true for some x in A. Now in this case, for us, what are the relevant statements when x is 3 and y is 1? This is true. And so are these statements. 5, 1, p of 9, 1. All of them are true because actually all of them are the same statement, and that statement is nothing but y is equal to 1. Okay. So that particular y, those values of y can be collected together, and that collection will be a set. That's what Axiom 3.6 says. So in this particular case, we see that there is only one such value of y, which is 1. So we get the singleton set 1. So in this case, we are replacing each element of A by 1, thereby getting the singleton set 1. So, axiom 3.6 can give us a set smaller than A. Smaller than A means smaller than the original set. In our case, the original set is A, that's why we have written A. However, note that in this place we cannot have a larger set than A. That's because every element of A is either replaced by exactly one element or it is not replaced by anything. So that's why it's not possible to have a set larger than A. But we have put smaller within quotes. Why? Because we still have not formally defined what we mean by smaller and larger. That we will do in section 3.6, where we study finite sets and their sizes, where we actually define finiteness, and there we will also see what infinite means. Basically, an infinite set will be defined to be a set that is not finite, but those things we will see then. Okay. Now, now it's not possible to always write this much to specify a set, so we abbreviate. We often abbreviate a set like, we can take the set from the previous example, the set of all y such that y equals the successor of x for some x belonging to A. Abbreviate a set like this as simply this. They mean the same thing. Or if we don't decide to use colon, we can write like this. Sometimes we use the vertical bar. Although I like to use, personally I like to use the colon, but they mean the same thing. They mean such that. Sometimes it's useful to use the vertical bar because if we are dealing with functions, then in some cases we may confuse ourselves with many columns. Now, one can use the axiom of replacement in conjunction with the axiom of specification, the previous axiom. To get a set like this. If x such that Px is true and x belongs to A in the following manner. We can use the two axioms together to create a set like this. How? We start with A. The set A is given to us. Then use the axiom of specification then use the axiom of specification to get this set. The set of all x belonging to A such that Px is true and then use the axiom of replacement to get this final set. Where we are replacing each element x in this set, not in A but in this set, by fx. So fx really means y in this context. Okay. Thus, we have the set. For example, we can apply this procedure to have this particular set. The set of all successors of n such that n belongs to, or I have written the condition first, right? N is less than 7 and n belongs to 3, 5, 9. So if you recall from the example before the one we have started this video with today, the actual, if we just simply write the successors of these elements, we get 4, 6 and 10. However, here this extra condition tells us that we cannot take n equal to 9. So that means this will be 4 and 6. Now, we have seen quite a few axioms so far. Enriching the class, each axiom enriches the class of sets by restricting it in some ways. So let us just quickly go through the axioms we have seen so far. The first one says that sets are objects. In particular, if we are given two sets, then we can legitimately ask whether one of them is an element in the other or not. The second one is the axiom which postulates the existence of an empty set, which later turns out to be unique because of our definition of equality of sets. The third axiom says that there are singleton sets and pair sets. The fourth axiom says that if we are given two sets, then there is a set which is known as the pairwise union or the union of them. So it is the axiom of pairwise union. The fifth one, of course, is the axiom of specification, or let me just simply write the word. It allows us to create a subset of a given set using some property or condition that the elements of the given set may or may not satisfy. It is the subset consisting of those elements of the given set that satisfy the condition. And then the sixth axiom is the axiom of replacement. It helps us replace the elements of a set by some other objects, possibly collect them together and call that collection a set. So these axioms so far have given us some sort of restriction on the class of sets. Now, at the same time, it's not just restricting the class of sets, it's telling us what collections are allowed to be sets. Okay, in that sense it's a restriction, but it is also introducing some things in the class of sets like the pair set, then using the singleton set, the empty set, then using the singleton sets and pair sets, we can create more and more sets. Then using pairwise union, we can create even more sets. Then using specification replacement, we can create more and more sets. Now there is a seventh axiom, which actually we have already seen when we studied the development of the system of natural numbers. There we made an assumption. If you recall, it was assumption 2.6. If you go back to that video and see this assumption, you will see that it just simply says that there is a system of natural numbers which satisfies the piano axioms. So when we made this assumption, we did not have the language of set theory. So there we said that we are just simply making an assumption which we will formalize using the language of set theory. So now the time has come that we formalize that thing, and that is going to be our seventh axiom. And this, like the other axioms, this one also has a name. So this is axiom 3.7. It's known as the axiom of infinity. We will see why it's called axiom of infinity, but let's just first go through the axiom. It says that there exists a set N whose elements are called natural numbers. An object 0 in N and a successor. I am putting this within quotes because it has to be italicized, it's being defined, right? We have already defined those things, or we can just simply keep it like this because the piano axioms will take care of it. A successor n plus plus belonging to n for each element n in n such that the piano axioms which are axioms 2.1 through 2.5 are satisfied. So by including this new axiom, we have introduced in our class of sets an example of an infinite set. That's why this is called Axiom of Infinity. It introduces the very basic infinite set, which is the smallest infinity in some sense. We will see these things when we study functions and when we go to finite and infinite sets. The list of axioms in this chapter ends here, but there are more axioms, the ones that involve somewhat more complicated concepts, and that will be studied in chapter 8. So we will see that. So the axiomatic set theory part in Tao's book this is the first one. In chapter 3 we only see the first part of axiomatic set theory. The second part will be seen in chapter 8. So let us just write what we have said just now. This axiom is the formal version of assumption 2.6 that we have already made. It's called the Axiom of Infinity. Because it introduces an infinite set, not just any infinite set, but the very basic infinite set, very basic type of infinite sets. Infinite set in the class of sets, and in this regard we will rigorously define what finite and infinite mean in section 3.6. So for that we have to wait, but for now we can think of finite and infinite sets like how we already know them, vaguely, not rigorously, but we have an idea of what finite and infinite mean when it comes to sets. Okay. And this axiom also tells us one more thing. You see, we have been using in many of our examples the fact, although we are not explicitly, we haven't mentioned it, but we are using the fact that the natural numbers are objects in set theory. Unless we say that something is an object in set theory, it does not have the right to be an element of some set. Okay. So this axiom includes in it that thing also, that the natural numbers defined using Peano axioms are objects in set theory. So the set that we have considered here, you see, in the example that we have seen today and the one in the previous part, in that example we started with the set this right 3, 5, 9. Now we cannot just simply take a set of any object just like that. It has to come from the axioms. It may seem somewhat strange, but that's how an axiomatic treatment goes of something. Everything has to ultimately come from the axioms. Now, how is this set a set? How can we justify that this is a set from the axioms that we have introduced so far? You look at this axiom 3.7, it tells us that these objects 3, 5, 9, etc. are objects in our set theory, or objects in the, I should not say in the class of sets, but in our set theory. They can be elements of sets. Since they are objects, so these singleton sets exist by the third axiom, because for any given object there exists a singleton set considering that object as an element. And by using the axiom of pairwise union 2 times in any manner that you want, either like this or like this. This union, this final union is also a set according to the fourth axiom, axiom of pairwise union. That's how we are getting this set. Okay, so once the mathematicians have come across Russell's paradox, that was the that told them that since any collection cannot be considered as a set, there are problems. So now they are taking their steps very cautiously, so cautiously that every set has to ultimately come from the axioms. So that's how this is a legitimate set. Okay, now it may seem like too much ado about nothing, but it is important, and the importance will be felt more and more as we go further. Now this section ends with this informal example. It is informal because it involves the notion of subtraction, which we have not formally defined yet. So this is example 3.1.33, and it's accompanied by the word informal. I will not write everything down, I'll just simply write the equation and say why this example exists. I mean, why it has been given, what is its significance. The set of objects n plus 3, where n is a natural number and it lies between 0 and 5, is equal to the set of objects 8 minus n, where n is a natural number and again n lies between 0 and 5 inclusive, including 0 and 5. You don't have to do much to see that this is true. You just put the values of n, write this set, write all the elements, express this set in what I forgot the name, what the hell, what this is in set builder method, roster method, tabular method. I don't know what happened to me today. So using in roster method, you write the set, you specify all the elements. The same thing you do with this, you will see that the two sets are actually equal. The point that this example is trying to make is that we should really distinguish between a set and its elements. One should not think that this set and this expression n plus 3 are the same thing. This in particular, this equation is not saying that n plus 3 is equal to 8 minus n. That's not what it is saying. It is saying that the set of objects n plus 3 that satisfy these conditions is equal to the set of objects 8 minus n that is also satisfying these conditions. Okay, so that distinction between a set and its general element should always be maintained or should be understood clearly. Otherwise, there will be a lot of confusion. Okay, so that's the point this example is trying to make. Tabular method, I forgot that name all of a sudden. Okay, now we look at the exercises at the end of this section. We have already solved 4 of them, the first 4 of them, but the remaining ones, let's just have a look at them one by one. So we start with the 5th one, exercise 3.1.5. Most of these will be quite easy, since we have already seen such exercises in our study of naive set theory. Let A and B be sets. Show that the statements that A is a subset of B, this is one statement, A union B equals B, this is the other statement, and A intersection B equals A are logically equivalent. Logically equivalent means if one of them is true, then the other two are also true. That's what we have to show. Okay, so let's see how this goes. Actually, it's very easy, but let us just go through it for once. How should I start? I mean, should I name these statements something like A, B, or C? Or let me just simply start it just like that. First, assume that A is a subset of B. Okay. We intend to prove that A union B equals B. Now we already know that B is a subset of A union B, right? This is something that, this is a property of union. We have to now show that the reverse inclusion is also true, that A union B is also a subset of B. Let X belong to A union B. Then X belongs to A or X belongs to B by the definition of union. Since A is a subset of B, X belongs to A implies X belongs to B. So, if X belongs to B, then fine. If X belongs to A, then this condition makes sure that X again belongs to B. So in any case, we have X belongs to B. Hence, we assumed any element in A union B, we have proved that that element must be in B. Hence, A union B is a subset of B. Now you combine these two containments and get equality. Thus, A union B is equal to B. So we have proved that if we assume this one, then we get this one. Next, assume the second one to be true. We now try to prove this one. Here also we already know something. I can't remember whether I have already solved this in night set theory or not. If I have already solved this, if we have